Topic 7E, finite difference analysis of transmission lines. So this lecture will be heavily electromagnetic, but I'm really trying to minimize the amount of electromagnetics that this involves. We're analyzing transmission lines, and to make a very long story short, a transmission line is a couple of wires that propagates an electromagnetic signal along the line. When we analyze these lines, we're interested in several things usually. One is to visualize the electromagnetic fields around it. And we can look at things at how far outside the line the fields extend. That gives us an idea of how close we can place other things without affecting the performance of the line. We're also interested in something called the characteristic impedance of the line. So if we're watching a signal propagate down the transmission line, if we look at the ratio of the voltage to the current on that line, that gives us the characteristic impedance. And it's not so much that an impedance that is high is good or low that is good or anything like that. Really what matters is when the line changes impedance, when there's a discontinuity and we start to get reflections. Usually we don't want that. Sometimes we do if we're making filters or things like that. Another property that we'll analyze is the effective refractive index. Refractive index is the factor by which a wave slows down relative to an electromagnetic wave in outer space. So the higher this effective refractive index, clearly the more interaction the electromagnetic fields are having on the line, and they're traveling slower. In order to get these parameters, we need two other parameters that are a little bit more fundamental that come from the electromagnetics, and that is the distributed inductance and distributed capacitance. If we think of two wires, they do form a capacitor and they do form an inductor. And really our electromagnetic analysis is evaluating the distributed inductance and distributed capacitance, and the other things fall out of that. If you followed everything I said there, you really have all you need to know about the electromagnetics. So let's begin this lecture. We'll divide this into several sections. This is going to be a long lecture, but I think it's important that it is all together in all one. The first thing I want to do, before we even get into the numerics, just describe at a high level how we're going to solve the problem. What equations will we use? Where do they come from? After that, we'll pretty much start all over again, but we will formulate our problem. That is, come up with the equations that we will eventually plug into MATLAB. And the first thing we need to do that is start with the basic electromagnetic equations and derive what we call the governing equations. These are the ones that we need to solve numerically that we'll use the finite difference method for. Which brings us to the last part of the formulation, which is where we take our governing equations, approximate them with finite differences, write them in matrix form, manipulate them, and finally get an AX equal B type of problem that we solve to get the answer. And then once we have the answer, we need to do some post-processing to calculate distributed inductance, distributed capacitance, characteristic impedance, effective refractive index, visualize the fields, etc. Given that, then we'll discuss implementation and some subtleties with that that is really specific to working in 2 dimensions and solving the equations and how to post-process them. And at the end, I'll give some examples. And these examples are useful because these are things that you can try to simulate and duplicate the results in the lecture here. Okay, now we're ready to officially begin. This first section, we're not talking about numerics or finite differences or anything else. We're at a very high level, really just describing the equations that we will be using and how we will use them to solve the problem. It really all begins with Maxwell's equations, and there are 4 of them. And here we're looking at these 4 equations in what's called time domain differential form. And these describe classical electromagnetics. What do I mean by classical? We're not worried about relativity or moving media or any of these other types of generalizations that we could make. So Maxwell's equations, if we look at those, and if we study the parameters for a while, what we see is that there's not really any material properties here. Interestingly, Maxwell's equations do not tell us directly how the electromagnetic fields interact with materials. Maxwell's equations is more quantifying what creates electromagnetic fields. How they interact with the materials comes from what are called the constitutive relations, and there are two of them. One describes the electric response of a material, and the other describes the magnetic response. I'm not going to go too much into detail here about what these equations mean. You can refer to some of the electromagnetics classes that I teach. And we're going to be manipulating these around and substituting into each other and really end up with one equation at the end that hopefully we'll understand. We don't necessarily need to understand everything about these equations simply to understand this from a computational perspective. We have some physical constants that describe our materials. There is the electric response of a material described by the permittivity. And we really can break this into two terms. Just the epsilon alone is called permittivity, but we can write this as the free space permittivity times a constant that tells us how many times higher the real permittivity is over free space. Sometimes this epsilon r, this relative permittivity, is called the dielectric constant, and it's a unitless number. We also have the magnetic response of the material. That's called permeability. So we'll have mu, and that can also be written as a free space permeability and a relative permeability. The relative permeability being equal to or greater than 1, and also another unitless number. So this is how we will describe our materials, and in our code, we will really exclusively use the relative permeability and relative permittivity. These are much more convenient numbers. These are numbers that will be usually between just 1 and 10. They're very easy. Whereas if we specified the actual permittivity and permeability, we have crazy numbers that are 10 to the minus 6, 10 to the minus 10 sort of thing, and they're just not as convenient to work with. So we will work with the relative permittivity and relative permeability. Interestingly, if we take the free space permeability and permittivity, we can actually calculate the speed of light from those. Maxwell was the first to do this, and that was a big deal in the late 1800s when he did that. For our analysis, we are going to make an electrostatic approximation. That is, analyze this at DC. Now, transmission lines can be used at DC, but they're not really. So why is it still sort of accurate to analyze these with the electrostatic approximation? And that's because the transmission lines are usually so incredibly small relative to the wavelength of the signal that the wave nature just can't manifest itself on the scale of the transmission line. And so the electrostatic approximation makes this a lot easier for us to analyze, and we actually get very accurate answers from this. So for the electrostatic approximation, we will analyze this at DC, zero frequency, and since we have time domain equations, what that means is anything that we differentiate with respect to time, that derivative has to be zero because it's static and not changing. And so we find our derivatives with respect to time, and we just simply cross them off of Maxwell's equations, and we end up with 4 equations for the electrostatic case. Another thing that we will be using so that we don't have to solve an equation with a vector quantity is something called the electric potential V. This is just a scalar number in volts. And very often the electric field and the scalar potential are confused for being two different things. There's only one electric phenomenon happening. There's just two different ways that we can describe that. We can describe that through the electric field or the potential. And if you want to know a little bit of a deeper story, I have some notes here over to the left. We have from Maxwell's equations for our electrostatics that del cross E equals 0. This del cross E is curl, and that basically says that the electric field cannot circulate in an electrostatics problem. So the curl of the electric field has to be 0. Well, from vector calculus, we know that the curl of the gradient is always 0, no matter what that function v is. And I'm looking at this equation. So if the curl of the electric field is 0, that means we can write the electric field as the gradient of some other function. And that other function, since it's scalar, is a lot easier to analyze problems. So we say the electric field is the negative gradient of the potential, and we throw the negative sign in there just to reinforce our sign convention with positive and negative charges and the orientation of the electric field. It's completely a definition thing. So the electric field is the negative gradient of the scalar potential, and we would like to convert everything over to the scalar potential, so we just have a single scalar differential equation to solve. We'll need to solve Laplace's equation. Actually, twice we'll solve it. One we will call the homogeneous Laplace's equation, and then also the inhomogeneous Laplace's equation. So what is meant by that? Homogeneous means all of the materials throughout our device are the same and constant. If it's inhomogeneous, it could be changing in potentially crazy patterns. So the most general equation is Laplace's equation inside of inhomogeneous media, and we want to derive that equation. So if we ignore charges, we have from Maxwell's equations del dot D equals 0. This means the divergence of D has to be 0. That's one of our basic equations. Well, we know from the constitutive relation that the D field equals the permittivity times the electric field. D equals epsilon E. So we can substitute this equation, the constitutive relation, back into equation 1 to eliminate the D field. And now we essentially have the divergence of the relative permittivity times the electric field equals 0. Now at this point, we would love to be able to take this epsilon outside of the divergence, because then we could divide both sides of the equation by that epsilon, and we would have just del dot E equals 0. However, we said this is inhomogeneous. That relative permittivity may be changing as a function of position. Therefore, when we take derivatives of it with respect to x, y, z, we would not get 0. So unfortunately, for the inhomogeneous Laplace's equation, that relative permittivity must stay there. Well, we know that the electric field is related to the scalar potential as E, the vector E, equals the negative gradient of the scalar potential. And we can take this equation now and substitute that back into equation 2. When we do that, we eliminate the electric field, and now we have a single differential equation just in terms of the scalar quantity V. So by solving this, we somehow describe our transmission line and build that into the relative permittivity. We can now solve this equation for the scalar potential, and it gives us a picture of the scalar potential around the line. Now for the homogeneous case, where the materials are constant, we can take that epsilon, the relative permittivity, outside of the del operation, and then we can divide both sides by the permittivity, and we're just left with now the divergence of the gradient. And we can combine those two operations, and we're left with the Laplacian operating on our scalar potential equals 0. So this is, again, Laplace's equation, but for homogeneous media. And it's a lot simpler than the equation on the previous slide. It's really the same equation. It's just that the equation on the previous slide was for general inhomogeneous media. Clearly, this is the easier equation to solve. So we've solved it. We've calculated the scalar potential. Once we have the scalar potential, we can calculate the negative gradient of that and get the electric field E. We can then multiply the electric field E by the permittivity and get the electric flux density D. Once we have E and D, we're now ready to figure out what the distributed capacitance is. So first, we want to know the total energy stored when we're viewing our transmission line as a capacitor. Well, since we know the E and the D field, it turns out the dot product of these two is the energy density. So if we integrate that over the cross-section of our transmission line, so it's a two-dimensional integration, we can get the total energy in that transmission line. Now from circuit theory, we can relate that total energy to the capacitance through this equation. If we know the applied voltage and the capacitance, we will know how much energy is stored in that capacitor. So essentially, we combine these two equations, and we can calculate the capacitance from the electric fields. Now, since we are only looking at the fields in the cross-section, the capacitance we get from this is what's called a distributed capacitance. So it's not a total capacitance with just units of farads. This is a distributed, farads per meter or farads per centimeter, or really whatever units you wanted to use. So there's a difference between the distributed capacitance and the capacitance. To get total capacitance, we would have to know the total length of the line. Not knowing the length, we're just calculating capacitance per unit length. So we have a way of calculating capacitance given our applied voltage simply by integrating the D and E fields in the cross-section of the transmission line. So here's where it gets a little bit weird. If we wanted to analyze a transmission line that had magnetic properties, we would have to go back to Maxwell's equations and use the magnetic equations to calculate that. Almost all transmission lines do not use any kind of material that has a magnetic response. So in this case, there's a clever trick that we can do. And if we look at the voltage and current signal on the transmission line, and we also looked at the materials that the transmission line is embedded in and pretended that there was an electromagnetic wave traveling through that, those two signals would travel at the same speed. And so that's what this first equation is saying. Well, we know what the equation is for the velocity in these both cases. In the case of a transmission line, the velocity along the transmission line is 1 over square root of LC. And the velocity in just a infinite medium is 1 over mu h times epsilon h, or 1 over the square root of mu h times epsilon h. And we can solve this for LC. Now from there, we'll solve this equation for L. So in other words, if we can calculate the distributed capacitance, we can just immediately from that get the distributed inductance. But there's a catch here. The inductance of the line should not be a function of the permittivity, because the permittivity is the electric response of the material. But we have permittivity here, and it seems like if the capacitance is a function of permittivity, so should the inductance. So something weird's happening here. And the answer is, it would be, but physically, the inductance does not see permittivity. So what we have to do in our simulation is remove all of the materials, just make it all air. In fact, we could make it any permittivity we want to. We just have to make it homogeneous. It's convenient just to put all air in there. Now that we've removed the dielectric, the inductance is not sensitive to that. And so we can calculate the distributed capacitance for this homogeneous case filled with air, and then from that, calculate the actual distributed inductance of the line. So we're just going through this intermediate distributed capacitance for the homogeneous or air case. Once we have the distributed inductance and distributed capacitance, and remember, to get those, we actually had to solve Laplace's equation twice. We'll solve the inhomogeneous case to get the true distributed capacitance. Then we'll remove all the dielectrics, replace it all with just air, the homogeneous case. And we solve that case using homogeneous Laplace's equation, from which we will get the distributed capacitance of the homogeneous case. And from that, we get the true distributed inductance of the line. But once we have L and C, square root of L over C, that's the characteristic impedance of the line. Then we can calculate the velocity of a signal traveling along the line. And then last, the effective refractive index of the signal on that line, all from L and C. So our simulation is most fundamentally calculating L and C. Once we have those, we can calculate these other properties. And once we know all these properties of a transmission line, a microwave engineer or circuit designer could go off and design a whole bunch of stuff. It's our job as the computational people to build the simulation simply to calculate those properties. We don't necessarily need to understand the electromagnetics behind those properties. So just to remind us, we have a two-step modeling approach. So on the left, I am showing a strange coaxial transmission line that has a dielectric fill that's split in half. There's a green and a yellow region. And I did that just to make it inhomogeneous. So the first thing we would do is remove all of the dielectrics. And we would build this onto our grid. And we're looking at a cross-section of our transmission line without any dielectrics. We solve this using the homogeneous Laplace's equation, from which we get the homogeneous distributed capacitance, from which we get the real distributed inductance of the line. Second, we do it all over again, but we put the dielectrics in there, the permittivity. And we solve the inhomogeneous Laplace's equation, from which we get the actual distributed capacitance. And then, of course, once we know L and C, we'll know everything else. So this is how we will analyze our transmission line. Step one, we will build a picture of the transmission line on a 2D array. And we'll remove all the dielectrics. So really, it's just the metals that we're drawing here. So that's step one. Build a cross-section of the transmission line without the dielectric. We will then solve homogeneous Laplace's equation, and we will do this using the finite differences. And we will get that scalar potential for the homogeneous case. Once we have that, we calculate the electric field E from the negative gradient. We will calculate the electric flux density D as the permittivity times the electric field E. We'll then integrate the dot product of D times E to get the distributed capacitance for the homogeneous case. And then finally, from that, we get the distributed inductance of the line. Now we essentially repeat everything all over again. We build our transmission line on a two-dimensional array, but now we include the dielectrics. Now that the dielectric is there and our permittivity is inhomogeneous, we solve the inhomogeneous Laplace's equation, and we will do this with the finite difference method, and we'll talk much more about that when we get to it. So now we have the scalar potential for the inhomogeneous case. So this is really the true scalar potential. If we wanted to plot what the scalar potential actually looks like, it's this answer, not the one from the homogeneous case. We just did a trick there to get the distributed inductance much more easily than doing a magnetic analysis. So for the inhomogeneous case, this is the true scalar potential. Once we have that, we calculate the electric field E as the negative gradient of the scalar potential. We can then calculate D as the permittivity times the electric field E. We'll integrate that and get the distributed capacitance. Once we have the distributed inductance and distributed capacitance, those are just two scalar numbers, we can get the characteristic impedance and the effective refractive index, velocity on the line, and probably other things that I'm forgetting about right now. Okay, so we just covered at a high level how we are analyzing transmission lines. We started with Maxwell's equations and derived the scalar equation. We're essentially solving for the scalar electric potential and using that to calculate the transmission line parameters. Let's start all over and derive the governing equations that we will use and then approximate with finite differences and eventually put everything in matrix form. So this step is just deriving the equations, not yet finite differences. That's the next step. So in the last section, we had Maxwell's equations. We then set our time derivative to 0 and Maxwell's equations simplified. And we also introduced the negative scalar potential. So these three equations is really what we're going to use to describe electrostatics. That's our starting point. So we have equation 1, 2, and 3. We can take our first equation and expand it a little bit. Our D we can write as a column vector of the x, y, and z components, and then the dot product would put our derivative operators in a row vector. So we've expanded our divergence equation into a matrix form. This is not really the matrix form for finite differences. We're still in an analytical closed form symbolic land. We have our D equals epsilon E, our constitutive relation. What I've done now is put square brackets around the permittivity. That term is actually potentially anisotropic, and it's a tensor, a 9 by 9 tensor. To make things simple for us, we are going to ignore these off-diagonal terms and set them to 0. That's a whole other discussion how to handle anisotropic materials. And I have information about this on other course websites if you're interested, but it's not something we're going to handle here. And then the electric field being the negative gradient of the scalar potential, we can write in a matrix form this way. So far, on the last slide, everything was fully three-dimensional. However, we're analyzing just the cross-section of the line. And the line is continuous, and we'll assume infinitely long in the z direction. So if we take the derivative of anything in the z direction, whether it's a material property or the electric field, nothing's changing in that z direction because it's uniform. So any derivative we take in that direction has to be 0 because nothing is changing. So we can go back into those equations we wrote on the previous slide and just start crossing off z derivatives and see what that means to us. So in our first equation, if we cross off the z derivative, what that tells us is that dz equals 0. So we don't even have to include it in that first equation. So we can reduce this first divergence equation to simply an equation containing only the x and y component. Now we look at the d equals epsilon e. And if dz is 0, we see that that also means ez is 0. So we only really need to retain ex and ey in addition to the dx and dy. But we simplified this constitutive relation a bit by doing that. Now we can look at the electric field being the negative gradient of the scalar potential. And if Ez is 0, we can drop off the z derivative. And we're left with a slightly simplified version of how to calculate the electric field from the scalar potential. So what we've gotten from this is the z component of both d and e is 0. And in fact, on a transmission line, we usually have what's called a TEM, transverse electromagnetic wave. And there's a larger story to really justify that. So I haven't done that quite justice here, but there's no need to. So here are our final governing equations. Here they are on the left in sort of a symbolic matrix form. And then on the right, we've expanded those matrices and wrote it as just discrete scalar equations. So both the left and the right set of equations are equivalent here. And so what we'll do is we'll start with these equations, approximate them with finite differences, convert them to matrix form, and then start combining them to get our single final matrix equation. Okay, so the last slide had our starting point for our finite difference analysis. We're going to start with those equations and put them in matrix form into a form that we're going to solve using finite difference method. So right now we're going to assume that our functions are discrete. And so think of how many things we have to keep track of. We have the x component of the d field, the y component of the d field, and we're not doing the z component of the d field because we learned that that's just 0. So we have dx and dy. Likewise, we have the x and y components of E. So we have ex and ey. We have the permittivity exx or epsilon xx and epsilon yy. So already we have 6 things that we need to make discrete and think of as storing on an array. And we have to figure out where these go. And we understand from previous lectures when we have multiple functions happening that we may have to stagger things. But looking at this first constitutive relation, there's no derivatives, there's no need for staggering. So on our grid anyway, we can put the x component of D, the x component of E, as well as the XX tensor element of the permittivity at the same point on our grid. We don't know where they are relative to the other ones yet, but we at least know that they will reside at the same point. We look at the other equation that has fallen out of our constitutive relation, dy equals epsilon y times Ey. Well, there's no derivatives here. We don't need to stagger anything, and so we conclude that the y component of D exists at the same point as the y component of E, which will exist at the same component as the yy tensor element of the permittivity. So far, it doesn't seem like we need any staggering, or at least nothing has told us that we need staggering. It turns out we will need staggering. It just won't come from these equations. Now we look at when we're calculating Ex from the scalar potential. And it turned out that the partial derivative of the scalar potential in the x direction gives us the x component of the electric field. Now we have a need to stagger things. On the right of this equation, this is how we would like to take our finite difference of the scalar potential. And so we only want to span one grid cell, just have one delta x here. That would place our Ex at the midpoint between where we're having our scalar potential. So right away we can write the V and Ex as alternating in the x direction somehow. Similarly, we can look in the y direction, and we also figure out that the scalar potential and the y component of the electric field have to alternate in the vertical direction. We still don't quite know yet how the x and y components of the electric field will fall with respect to each other, but we at least know that in the x direction, V and E sub x alternate, and in the y direction, V and E sub y alternate. So it turns out, because we have the same V in the x and y directions, they have to be co-located. So we'll set up the grid this way, and there's probably other ways we can do it, but I'm going to place the scalar potential at the origin of each cell. So here's the first cell, and I'll place the scalar potential in that cell right at the origin, which would take the x component of E and place that halfway down the cell in the x direction, and the y component of E halfway down the cell in the y direction. So when we start looking at these other components, these actually belong to the next cell down, and these terms, V21 and EY21, belong to this next cell, and so on. I'd suggest pausing the video for a moment and staring at this and see how this staggering lets us write the finite differences how we would like to write them, not spanning 3 or 4 cells, but just one cell. Now, drawing the grid this way is maybe a little bit misleading because we have some of the components right on the edge of the cell. We will truly place them here, but let me show you an alternative way to draw this. So this new way to draw it really does not tell us accurately where those components are within the cell, but it more intuitively shows where they are within the cell. So for the next few slides, we're really going to proceed with what I'm showing on the right here, because it just more intuitively shows what cell those components belong to. But the grid on the left is really what we're going with. So we have our governing equations on the left, and we're not putting these in those symbolic matrix form yet. We expand them into just the standard ordinary differential equations. And we could approximate these with finite differences. However, we're also armed with what we've been talking about in the previous lectures, and we could have just immediately jumped from the analytical equations on the left to those equations in matrix form on the right. But maybe it's useful to show the finite differences that we're actually using. We needed to look at those because that's what dictated the grid that we needed. So my notation here, if I'm showing a lowercase bold letter, that's a column vector. And in this case, it's our unknowns. The capital letters are square matrices. So this will be our derivative matrix of an electric field quantity in the x direction. And from the previous lecture, we know what those look like. So all lowercase letters are column vectors. These epsilon naughts, those are just a single scalar constant. These epsilons are also square matrices. They're doing a point-by-point multiplication onto the electric field column vectors. And then finally down here we have our derivative matrices for the scalar potential. And hopefully from the last lecture, we're comfortable now having different derivative matrices for our different functions due to the staggering on the grid. So what we did analytically was start with our essentially 3 governing equations, and we started substituting them into each other until we finally got this one equation for the scalar potential. So when we're doing this numerically, what I usually like to do is very early in the process in our very starting equations, jump to matrix form, and then from there start combining them like we originally did with the analytical equations to eventually get one matrix equation just in terms of the scalar potential. So on the left were our analytical governing equations, if you will, and on the right now in block matrix form are really the numerical equivalents of that, the matrix equivalents of that. And so we'll substitute these into each other the same way we did the analytical equations. So let's go ahead and do that. So we have our first equation. This is the del dot D equals 0. But we also have the constitutive relation D equals epsilon times E. So we have an expression for the D fields that we can substitute in and replace the D fields. And we can simplify a little bit. And now we have one final matrix equation just in terms of the electric field E. We no longer have the electric field D reference. We've algebraically eliminated it. We didn't set them to 0. We just algebraically eliminated the D fields. Well, there's one other thing we can do. We can write our electric fields in terms of just a single scalar potential. So we can take this expression for our electric fields, replace the electric fields with the negative gradient of the scalar potential, and simplify, and we end up with one final matrix equation with a single scalar unknown. And this is the inhomogeneous Laplace's equation. So we did this analytically. We ended up with this as our inhomogeneous Laplace's equation. This really is the matrix form of this equation. And we could multiply that out, but we don't need to. Why not just leave things in their simple block matrix form? We can build them that way, we can use them that way, and it turns out it's more convenient. So that's the inhomogeneous Laplace's equation. Now for the homogeneous Laplace's equation, our permittivity is just 1 everywhere because we set it all to air. So this middle matrix really reduces to the identity matrix, and our homogeneous Laplace's equation is written this way. So we now have our 2 matrix equations that we will somehow solve in MATLAB. We need to back up now and talk a bit about how we're actually going to build the device on the grid. Now, from prior homeworks and prior discussion in this class, we had our dartboard homework and we did some other things. We learned a lot of techniques for building geometries on an array. And it's time to build on this a little bit to make some things easier. So our basic strategy for a transmission line, we are showing a microstrip transmission line here. So a microstrip transmission line is just a single circuit trace on a printed circuit board. So we'll typically have a strip of metal on top of a dielectric like FR4, that's the green stuff you normally see on a circuit board, and a ground plane underneath of it. Now we will also make it grounded all the way around. And this has to do with the fact that due to our staggering, our boundary conditions are not symmetric, so we have an asymmetric problem. And if we were to calculate the electric fields, they would look slightly pulled to one direction. So what we can do is just simply surround everything by metal, and that makes our problem look symmetric. It does not make it more accurate, it just makes it more visually appealing. Now, a circuit trace on a circuit board is not surrounded by metals, and by putting metals close to that, we're changing the characteristic impedance of the line. So the way we compensate for that is we have to add some space on the left, on the right, and on the top. We have to make sure that these metals on the left, the top, and the right are far enough away that it doesn't affect our answer. This is another convergence thing. How do we know how far away? Well, a rule of thumb is, however wide your line is, make these spacer regions 3 times that. But that's just a rule of thumb. That's just a good first guess. It really reduces to a convergence thing. We'll make a first guess. We'll get our characteristic impedance, distributed inductance, distributed capacitance, and then we'll make the spacer regions larger, and then larger more. How does our answer, at what point does our answer stop changing much? And then we know that we have large enough spacer regions. So this is the overall grid strategy that we'll use. In our code, we are going to build 4 arrays to describe our transmission line. A transmission line has 2 or more conductors. We're really only analyzing transmission line here that have 2 conductors. So we'll call one the signal and one the ground. So we are building 2 two-dimensional arrays. We'll put zeros everywhere, but we'll put ones in those arrays where we're placing our metals. So if we're describing a microstrip line on the signal, we just have ones over a little strip here. And then the ground, we definitely need the ground on the bottom, but just to make things look pretty, as we mentioned, we'll also put the ground all the way around. We just need to make sure that our grid is wide enough and tall enough that placing the metals on the left and the top don't affect our answer. Now, another thing that will happen, in reality, if we look at the thicknesses of our metals, they're very, very thin. And if we make our cell spacing small enough that we're actually accurately representing the thickness of the metals, we're going to need many, 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 many points in our transmission line. So a good trick, a good approximation is just make the metals 1 cell thick. Even though that will usually be much thicker than they actually are, we still get pretty good answers out of this. Okay, so we have 2 2D arrays. Each one describes our different conductor, our signal and our ground. Well, we need 2 other arrays that describe our relative permittivity. We had the epsilon XX and the epsilon YY. Now, why do we have 2 of them here? Well, remember, just due to our finite differences, they just fell at different points. So even though we might be describing something within the same cell in our grid, if there's some kind of curved boundary slicing through the middle of a cell, we could actually have our X component of the electric field inside one material and the Y component inside of a second material. And so we need these 2 different permittivity arrays to describe that case. Now, they will look very similar. They may just differ around where a boundary is. Now, this can get very confusing to do for curved geometries and how you sort all this out. And I have a very neat technique to show you that will make that very simple. But in the end, we're coming away with 2 more arrays describing the permittivity at each point, and they should look roughly the same. And in the case of the microstrip, they look exactly the same. So the lowest number we can have for a relative permittivity is 1. So I usually like to just initialize these arrays with all 1s, and then go ahead and just fill in wherever there's a dielectric material where the dielectric constant or the relative permittivity is greater than 1. But doing this goes back to our techniques of building geometries into arrays. So if you haven't been through that, I definitely recommend go back and review those skills so that you can build arbitrary geometries into these grids. Okay. So ultimately, we are after two matrices that are diagonal matrices, the epsilon xx and epsilon yy. Step one, which we talked about on the previous slide, is to build ERXX and ERYY. And here I'm just mentioning something called the 2x grid technique. This is something we'll talk about a little bit later. And this is a technique for handling when you have these curved geometries that may slice through the middle of a cell, and we got to figure out where those boundaries lie. But in the end, we just come away with our two 2D arrays. So we have our arrays. So then what we want to do is reshape those 2D arrays and make them column vectors. We will then declare them as sparse. And then we'll take our sparse 1D arrays and make them in a diagonal in a large square matrix. Now, it turns out I like to do all of these at the same time. So in just 2 lines of code, I've formed my diagonal matrices ERXX and ERYY. They started as 2D arrays, but I reshaped to a column vector, declared it as sparse, and placed those as a diagonal in a square matrix. I always do that in 1 line of code. So we've built our 2 permittivity arrays and then made them diagonal matrices. Now they're ready to go into our matrix equations. So we are going to have a matrix algebra problem. That's Laplace's equation. It'll be a big matrix operating on our scalar potential, and that will equal 0. And that's not solvable. We need to do something about that. And the reason that's not solvable yet is because we have not yet told the problem what voltage we're forcing our metals to. And that's what we're starting to talk about here. So we're going to create yet another 2D array that will have zeros everywhere, except where there are metals, we're going to say what voltage we're forcing those metals to. So in this case, our ground we set to 0 volts, and our microstrip line, our signal line, will set to 1 volt. We always want the difference between these to be 1 volt. If we do more than that, we can still formulate our code correctly, but we just need to account for that when we calculate our distributed capacitance. What you'll see is in our equations, we'll make the assumption that there's only 1 volt applied between the signal line and the ground, and that simplifies the equation a little bit. Not such a big deal to fix that, but you'll see when we get to that. So right now we have a 2D array, zeros everywhere, except where there's metals, the number is saying what the voltage is that we've applied to that piece of metal. So we'll take that 2D array and reshape it this way to get a column vector. Okay, now let's talk about this 2x grid technique. And this can be a little bit confusing. However, it's more confusing to try to sort out where the epsilon xx and epsilon yy go when you have curved geometries. So this simplifies that process. So here we go. So we start off with our ordinary grid. Since there's a 2x grid involved, we'll call our ordinary grid, or really the only grid that actually exists, our 1x grid. And so in this case, I did a very small one, 5 cell wides, 6 cells tall, and we made the grid spacing in both the x and y directions 1. So that's the first part of our MATLAB code. That defines everything we need to know about our grid. Now at this point, we just need to be reminded of where these different functions go. So remember, the blue dots is where we're storing our scalar potential, and the red and the green arrows are where we're storing the x and y components of our electric fields. And so I'll keep these here just to remind us where things are. So notice, due to the placement of our fields, it's kind of like we're getting twice the resolution on our grid. And in fact, if we describe the same physical amount of space but with twice as many points, so we bisect all of our cells and create a grid with twice as many points, we can see that those field components actually fall exactly on this grid that has twice as many points. This is our 2x grid. So if I'm going to build geometries that are curved and crazy, I'm actually going to create a grid that has twice as many points, build my device on it, and use that to figure out where everything lies. And you'll see this with some animations following. So now let's say I want to create a cylinder. That's a nice curved geometry. And I want to describe that ultimately in my epsilon xx and epsilon yy arrays. But we don't have that. Right now we just have one grid that has twice as many points as our true grid. And we want to build a cylinder on it. So for right now, I will ignore everything I know about the epsilon xx and epsilon yy arrays. I'm just thinking about this one grid that has twice as many points, and I will build the cylinder on it. And I'm calling that ER22 for relative permittivity, when the 2 there is reminding me that is the 2x grid that I've just built this cylinder onto. So I'll get rid of the outline. And you can imagine using mesh grid or a variety of other techniques. And now we have a cylinder built onto that 2x grid. From this, we need to extract our epsilon xx and epsilon yy. So looking at our 2x grid, we want to extract our epsilon xx. We know they fall where the x component of the electric field lies. That's on the red arrows. So what we're going to do is build a 5x6 grid and pull off the material values everywhere we see the x component of E. So we have no material, no material, no material, no material, no material. So in the entire first row of epsilon xx, we have no material. No material, we do have a material, do have a material, no material, no material. And that will form the second row of our epsilon xx. Let's go ahead and animate this. So we pull all of those points off, and we now have our ordinary grid for epsilon xx. And while that seems crazy, it's done in just one line of code in MATLAB. We're just pulling off from this ER2 array everywhere the x component of the electric fields reside, and that is our epsilon xx array. Now we want the epsilon yy. So we're going to look everywhere there's a green arrow and pull off the materials from those points. Let's go ahead and animate that. That is our epsilon yy array, and we can do that with just one line of code in MATLAB. So we built the cylinder on our single 2x grid. We called that ER2, and then from that we extracted epsilon xx and epsilon yy. We're back to our ordinary 1x grid now, and we can forget about the 2x grid. So here's a good picture of what we come away with. If we've done it properly, here's our two arrays. Now they look similar. They're both describing a cylinder, but what we can see is that they do look a little bit different at the edges. Because we only use so few points here, they look strikingly different. As our grids become more realistic, maybe 100 by 200 points, the differences between your epsilon xx and epsilon yy are much more subtle. But we can see some differences at the boundaries. So the code on the right is everything we had to do to build our epsilon xx and epsilon yy arrays using the 2x grid technique. Now it is a hugely common mistake for students to apply the 2x grid to other parts of the code. That is only a trick that we used to build the ERXX and ERYY arrays, which are back on our standard 1x grid. So after that, it does not exist. If you're using 2x grid for anything else, you're doing it wrong. Once we have epsilon xx and epsilon yy, anything 2x grid doesn't apply. It no longer exists. So you can just delete everything about your 2x grid at that point. So don't make that mistake. It's just a trick to get epsilon xx and epsilon yy. It's not used anywhere else. Okay, wow. We've been through a lot of stuff. We've derived our basic matrix equations. We've discussed how to build the device onto the grid, which becomes those sparse diagonal epsilon xx and epsilon yy matrices. Now let's talk about solving it. So we have our first inhomogeneous Laplace's equation. We discussed the 2x grid technique and diagonalizing these epsilon arrays. We know how to make these derivative matrices for a staggered grid, and we have everything now to build this equation. Now, if we try to solve this for V, we essentially have an L times a V equals 0, and so when we try to solve that, our scalar potential is just 0. We get a trivial solution. That is because we have not yet applied those voltages. We talked a little bit about it in terms of that array of forced potentials, but we haven't talked about how to incorporate that yet. But we have arrived at our first matrix equation. When we apply the voltages, it turns out the 0 over here becomes non-zero, becomes a B. And this will describe how we force things. And now we can solve that for the scalar potential. So the question is, how do we construct B? And it will turn out that we also have to modify L. So we have to change L and B to build in our forced potentials. And by forced potentials, I'm talking about the voltage that we apply to our metals. Here's the basic concept. What we want to do is look at our matrix equation, which has a whole bunch of numbers, our column vector of unknown potentials, and it's starting off as all zeros over here. What we want to do is look through our entire grid, and every point where there is a metal, we're going to go into L, zero out the entire row, place a 1 in the diagonal position, and then over here, put the number that we're actually, the voltage that we're actually applying to that point of the metal. And what we've essentially done is thrown out the finite difference equation that will be written there and just replace it with a very simple equation saying the potential at that point equals 6 or 7 or whatever it happens to be there. And so you can imagine setting up a big loop going through your grid. Everywhere there's a metal, zero out the row, insert a 1 in the diagonal or the pivot position, and then over in that B column vector, putting in the number that you're actually forcing it to. Now there's a fancier way of doing this. And it turns out in MATLAB it's much faster. And it's also easier because the arrays that we've already calculated make constructing these automatic. We don't even really need to do anything extra. But the two extra things, we need a force matrix. We'll talk more about what that is, but it's essentially a map to tell us where we're actually forcing potential. So it's a map of where the metals are. And then the force potentials. This is the function we talked about earlier. That's all zeros, except where there's metals, we put a number there of the actual voltage we're forcing to. So the force matrix is just identifying where the metals are. That force potential function tells us the voltage that we're applying there. So there's a difference. So the first thing we need to do to L is zero out all of the rows where there's metals. Well, that force matrix tells us where there's metals. And we want to zero out those rows. We take the identity matrix, subtract the force matrix, and if we pre-multiply our original L, we get another L where all those rows are zeroed out where there's metals. Well, we don't want to completely zero. We want to put a 1 in that diagonal position. And we can do that simply by adding the force matrix to that. When we do that, we get our modified version of L. So L prime is our final version of L. We still have to do B. And it turns out B is just the force potential matrix pre-multiplying the force potential function. So that's it. That's how we get L and B. Now we're ready to solve. Let's try to visualize what's in the force matrix. Remember in the beginning, we built two arrays describing where the metals are. One of them identified where our signal was. The other identified where the ground was. Both of these arrays were all zeros, simply with ones placed in the diagonal position. So our force matrix, the first thing we can do is OR those two things together. So now we have a map of just where there's metals. We're not differentiating between signal or ground, just where there's metals. And then we can make that a diagonal matrix. So that's why I said these are really automatic. Since we've created these two arrays describing our two metals, we simply just OR them together and diagonalize it, and we have our force matrix. So it's very rapid to calculate given those two arrays of where our metals are. Okay, so we backward divide L backward divide by B, and we have our scalar potential. Once we have the scalar potential, we calculate the negative gradient of that to get the electric field intensity E. So now we need to do a numerical differentiation to do that. And since we've already constructed these derivative matrices that would do that, why not just use them? We could also set up a big double for loop to do a numerical differentiation across our grid. But since we already have those derivative matrices, why not just use them? So that's exactly how I do it. So I just use those, calculate the negative gradient of the scalar potential, and I have the electric field E. Somewhere along the way, we built the tensor for our permittivity, and we can pre-multiply what we just calculated for the electric field E, that tensor pre-multiplying the electric field E, and get our electric flux density D from that. Now we know all of the electromagnetic fields. Now we can think about integrating to get total energy, to get distributed capacitance. So on this slide, we solve for pretty much all of our unknowns. The scalar potential, from that we got the electric field E, from that we get the electric flux density D. One thing I want to point out here, strictly speaking, there should be an epsilon naught out here, because these terms are the relative permittivity. And from a purely mathematical perspective, the epsilon belongs there. But because that epsilon is a very small number, it makes D and E very different orders of magnitude. So I like to not put it there. We'll need to put it back in when we calculate the distributed capacitance, but I don't use that at this point. So we're pulling that out, and we'll put it back in slightly later. So the MATLAB code looks something like this. We calculate our scalar potential as L backward divide B, and this is the L and the B after we've incorporated our force potentials. Once we have V, then the negative gradient gives us our E. Well, at this point, we may want to pull out the EX and EY separately. And so just the E is a column vector of two column vectors. And so the top half is our X component of E, and the bottom half is the Y component of E. So we pull off the top and the bottom halves from E. And now we have column vectors describing EX and a column vector describing EY. Don't forget, our output now is just column vectors. We can't directly visualize those. We need to reshape those back to our 2D arrays. Once we do that, then we can go to MATLAB. We can call ImageSC or P-color and see beautiful pictures of our scalar potential and electric field around our transmission line. But don't forget to reshape. That's an easy mistake to make. Okay, so we derived our equations. We went to matrix form. We solved our matrix equations, and we got the electric fields. Electric field E, electric field D, and scalar potential. From these, we want to calculate the transmission line parameters. We're now post-processing. The real simulation's done. We're just analyzing the results to get our meaningful parameters. So, distributed capacitance. Remember, this comes from when we solved the inhomogeneous Laplace's equation. So the D and the E here are the D and the E that result from analyzing the inhomogeneous Laplace's equation. Now, when we talked about this equation at the beginning of the lecture, there was a 1 sitting here. This is where I'm reincorporating the epsilon naught. Strictly speaking, the epsilon naught does not belong here. It belongs in the previous equation, but it's good numerical practice to keep your variables normalized as long as possible. And since this is our very last calculation, that's where I put in that ugly constant epsilon naught, which is 8.854 times 10 to the minus 12. That's an ugly number, so it goes in at the last point. This V naught squared, that's the applied voltage squared. So as long as we're only applying 1 volt, that V naught squared is just 1, and that equation simplifies considerably. So we need to do a numerical integration, a numerical double integral, to calculate our distributed capacitance. But using discrete integration, this is super easy. We have our dx and dy stored as a column vector, our ex and ey stored as a column vector. So if we take the transpose of d, that makes this a row vector, and multiply it by e, we are doing effectively a point-by-point multiplication of d and e, and it's calculating the dot product for us and adding them all up. And so all we need to do then is the delta x and delta y, that's our dA, that's the size of each cell. And of course, there's an epsilon naught that plugs in here. I put these in parentheses just to speed up the calculations. Otherwise, if I put it up front, it would probably multiply that for every element in D, and it would just take a while. So I do this dot product to get a single number and then multiply by that, and it's a slightly faster calculation. Now in MATLAB, what does that look like? It just looks like this. Remember, this is the D, that's the column vector of 2 column vectors. This is the E, that's a column vector of 2 column vectors, both containing the x and y components. So the dot apostrophe, that's just the transpose, which makes D a row vector, such that when we have our row vector times a column vector, it does a point-by-point multiplication and adds them all up. And that's how we get distributed capacitance from D and E. One line of MATLAB code. Our distributed inductance. Very similar to last slide. We will solve the homogeneous Laplace's equation, from which we get the electric field E, the electric flux density D for the homogeneous case. And we'll do this same dot product, add them up, and multiply by epsilon delta x and delta y. So we get another distributed capacitance, but just for the homogeneous case. So this is not the real distributed capacitance. This is just our intermediate term to get the distributed inductance. And that's the last step. So there might be a background permeability, but it has to be homogeneous. And we divide that by speed of light squared, and also divide by that homogeneous distributed capacitance. That gives us our distributed inductance of the line. If we have distributed inductance and distributed capacitance, the square root of L over C is our characteristic impedance. The speed of light times the square root of L times C gives us our effective refractive index. And that tells us how quickly the signal will be propagating along our transmission line, how quickly it would accumulate phase. So that's really it. A lot of stuff to take in, and you'll probably have to watch some sections over and over to really understand it and practice it. Try to code it, ask questions. But what I want to do now is show you some examples so you can get an idea of what the input looks like, what the output looks like, and start to get a feel of the types of numbers that you should see. What are the orders of magnitude for distributed inductance, capacitance, and things like that. So let's go ahead. Here's an example for what I call the weird coax. So the weird coax is one that's a coaxial line, but the dielectric is split into two. And this is simply to exercise having two different dielectrics. Now in this example, I've set them to be the same value. So we will still build this as if it's different, but since we put in the same number, it really is a constant dielectric fill inside the transmission line. So I gave all the dimensions for radii, for relative permittivity. We are ready to solve. The picture on the left is a three-dimensional view of our coax, but if we look at it straight on, this is what a cross-section looks like. And this is what we build into our array to analyze the transmission line. So that's step one. We just choose the line and collect all the numbers so that we know everything about it and we're ready to analyze. Okay, now we need to build, well, 4 arrays, but since now we have this 2x grid technique, we can think of this as 3 arrays that we have to build. We have 2 arrays on our standard grid describing our 2 metals. So in this case, we have our center conductor, and then we have one with our outer conductor. And before we talked about the microstrip, we talked about the edges of the grid needing to be sufficiently far away. Well, for a coax, everything's confined within the outer conductor. So we don't really have to worry about the distance from the outer conductor to the edge of the grid. So we only have to worry about that if the fields of the transmission line are exposed to the outside world. So we can use our mesh grid techniques and we can build both of these. And then we can also build the dielectric fill, but that's done on the 2x grid. So there's twice as many points on that grid as on the ones describing where our conductors are. And then from this 2x grid, we get our 2 1x grids, that's epsilon xx and epsilon yy. So we get our epsilon xx and epsilon yy from the 2x grid, we diagonalize those, and then lump those into a single tensor quantity, which also itself is a large diagonal array. Now we need our derivative matrices. So hopefully by this point you will have written this function TLDIR, or transmission line derivative matrix builder, TLDIR, and we give it 2 parameters. We give it an array of 2 numbers saying how large our grid is, then another array of 2 numbers, that's our resolution of the grid. Given that, it will build our derivative matrices, and we're using Dirichlet boundary conditions inside of this function. So, but since we have 2 functions now, our v and our e, when we put these together, we're actually going to have slightly asymmetric boundary conditions, and this is another reason why we put our ground for the microstrip all the way around the outside. But just remember, without that, your fields could look slightly asymmetric if you have an exposed line and don't put a metal all the way around. Okay, so we call TLDIR, we get our 4 derivative matrices. We've already diagonalized our materials. We now have our derivative matrices. We're ready to build and solve our matrix equations. So we'll do the inhomogeneous Laplace's equation first. So 1 line of MATLAB code to build L. And if we were to visualize it, it looks something like this. And that's very typical of solving a differential equation. It's a banded matrix with some bandwidth. We will also need L for the homogeneous Laplace's equation. And it's a copy and paste of what we had above. We just don't have that ER tensor. Or really that ER tensor is an identity matrix. Okay, so we've built L. Now we need to build in the voltages that we're forcing on our metals. So given these 2 arrays containing our 2 conductors, I'm calling it conductor inner and conductor outer. When we did the microstrip, we had signal and ground. So I just named them something slightly different, but I can still OR them together and get an array that's just a map of where the metals are, then make that a diagonal matrix. Also from these 2 arrays, I can create my force potential function. Remember, this one is zeros everywhere, except where there's metals, it's the voltage that we're forcing the metal to. So the inner conductor, I multiply by 1 because I want to force that to 1 volt. And the outer conductor, I multiply by 0 because I want to multiply it, or want to apply 0 volts to it. Now, technically speaking, I don't have to do this because it's already zeros. I just like to write that so I can visually see, okay, I'm applying 1 volt to the inner conductor, 0 volt to the outer conductor, And I can make sure that overall between the two conductors there's 1 volt. Once I have those, now I can modify my matrix equations that actually forces those potentials. So first I'll need the identity matrix. I modify both of my L's for the inhomogeneous case and the homogeneous case. Remember what's happening in those equations. We're zeroing out the rows. We're throwing out the finite difference equation that would be there, putting a 1 in the pivot or the diagonal position. And then both the homogeneous and inhomogeneous will use the same B column vector. So I only need 1 of those. And that's simply my force matrix times my force potential function reshaped to a column vector. I'm now ready to solve my matrix equations. So that's what's done in this step, 2 backward divisions. Interestingly, everything in this code up to this point runs very fast. So the shortest lines of code in your program is actually where you'll spend most of your computation time. And this isn't huge. You might spend 5 or 10 seconds here. If it starts to get longer than that, something is probably wrong. I'm not making you do that. For extremely large problems, and if your computer has enough memory, you could choose that and make it take that long, make it take 20, 30, even a couple minutes. But nothing in this class will cost you that much. So we backward divide, and now we have the scalar potential for both the inhomogeneous case and the homogeneous case. Given the scalar potential, we need to calculate our electric field E. We're doing this once for the inhomogeneous case, so we have the inhomogeneous electric field E, and then also for the homogeneous case. So 2 lines of code for doing that. So we calculate those from our scalar potential V. Then last, we need the D fields, and we do that simply by pre-multiplying our electric field by the permittivity. Now for the homogeneous case, the permittivity is just air as an identity matrix, so D just equals E. And so 2 very simple lines of code to get our D field from the E field. Now we're ready to calculate our distributed capacitance. And here's where we do the numerical integration for the inhomogeneous case. So we take our inhomogeneous D and E and do our dot product to get the numerical integral. This is a discrete integration. And notice the V naught doesn't appear here. We're just assuming V naught is 1. And this is where if V naught wasn't 1, you wanted it to be 3 or 6, we would have to include it here. Is that a big deal? Absolutely not. I just chose not to do it. We do the exact same thing using our homogeneous D and E, from which we get the homogeneous distributed capacitance, and then from that we'll get our distributed inductance. And again, in that equation, the V naught is not there. We would be having to divide by V naught squared, but since we've forced the 1 volt being applied between our inner and outer conductor, we don't need it there. And it's always good practice to apply 1 volt. I don't see a need to apply any more voltage than that. But if you did, you would just need to include it in that equation where we calculate the distributed capacitance. Well, now we have the distributed inductance, distributed capacitance. Square root of L over C gives us our characteristic impedance. Speed of light times the square root of L times C gives us our effective refractive index. And our analysis is not quite over. Remember, visualization is the key to computation, and so we want to visualize all of this stuff. A big mistake, and I make this all the time too, remember all of these functions come out of our matrix problem as column vectors. And if we were to just plot that, we'd see something like this, and we'd go, what on earth is that? Well, we have to reshape it back to a 2-dimensional grid. And if we do that, now we see a nice picture of the scalar potential. And this is simply a function that goes from 1 to 0. And it goes, eventually fades linearly from the inner conductor to the outer conductor. That's our scalar potential. So easy thing to forget, reshaping it back. We have two. We have the homogeneous scalar potential and the inhomogeneous. I don't really see a need to visualize the homogeneous scalar potential other than maybe just to make sure it's working, but that is not the real scalar potential of the problem. The real scalar potential is the inhomogeneous one, or the one that we calculated from the inhomogeneous Laplace's equation. Well, we can also visualize the electric field. We can use the quiver function and show the vector nature of it. And for this particular analysis, giving these dimensions and permittivities, here's the L, C, and Z naughts that I get. And by the way, these numbers pretty much stay the same for all transmission lines. So that doesn't mean you're always getting 361 nanohenries, but it's usually on the order of, 50 to 500 nanohenry per meter, in that ballpark. Capacitance is in the tens or hundreds of picofarads. And we need to do per meter because we're only analyzing the capacitance inductance in the cross section. Well, the length also changes things. And so if we had the length, we could calculate total capacitance and total inductance. Since we're only analyzing the cross section, it's a distributed inductance and distributed capacitance. Characteristic impedance in this case ended up being 71.5 ohms. And impedance is usually on the order of 20 to, let's say, 150 ohms. 50 ohm and 75 ohm are very common impedances. And the effective refractive index, 1.5. And that's always, 1.5 to 2-ish kind of range. And you could be simulating something completely crazy that has much more extreme values. But to within an order of magnitude, these are very typical numbers you'll see for transmission lines. Here's another case where I did actually make the two permittivities on either side different, and we can see how that affects things. It changed the distributed capacitance, distributed inductance a little bit, but notice we're still in that ballpark, the hundreds of nanohenries per meter, the hundreds of picofarads per meter. Our characteristic impedance went down a little bit. And why did that go down? That's because we increased the permittivity, which gave us a higher distributed capacitance. And since impedance is the square root of L divided by C, a higher capacitance gave us a lower characteristic impedance. And the effective refractive index went up simply because we're using higher permittivity values. That is slowing down the wave. So here are the dimensions. And here's what my array looks like. You can see the inner conductor, outer conductor, the two permittivities. So in a sense, I've superimposed all of the arrays that you have to generate, but it gives you an idea of the arrays you need to make. I got my potential, and here's what the electric field looks like. Again, using that quiver command, which I like to show the vector nature of the electric field.